this is Ladyada.
Hey everybody, welcome to my desk. Happy Sunday. Shout out to all my locksmiths out there. We're going to do a video about some stuff I've been working on. It's been crazy. Every January, everybody kind of wakes up and is like, oh, time to do stuff and ask Ladyada to do things. So it's been kind of bonkers, but that's good. A lot of stuff spinning up, a lot of projects happening. Let's start by going to the overhead, show off some hardware.
Ooh.
New Sparkle Motion final PCBs are here. So this is the mini version. Remember, this was the big version that we designed. And then I was like, well, I want a mini version as well. And it's actually a little easier to fab the mini version because it doesn't have the through-hole stuff. It's also just more compact. So this is a 4-layer board with 2-ounce copper, ESP32 on the back. Yeah, there's a lot of stuff to do with the antenna, but I think it'll be okay. 4-amp fuse, I2S microphone, level shifting output, a bunch of little breakouts, USB-C, USB serial converter, I2C out and in, and then a 1 digital analog input output plus 1 pin, 1 NeoPixel. This is the microphone, and this is the pin 0 and reset. Even though you don't actually need the reset in pin 0 because it auto resets through the serial converter. Pin 0 can be also used as a button input, and I thought it would be just nice to have. So this is this board. So it's the mini version. Doesn't have the 12-volt USB PD or DC input, but that's like the trade-off, right? I wanted to make something really, really tiny for wearable projects. So this would be it. And then you would power it from a USB battery, like a lipstick charger type thing. And you would just plug into USB-C, and then you get like an amp or two. So it's good for like amp or two portable projects. Again, you just plug into USB-C, a USB battery pack to charge it. So that came in. So we're going to work on the tester this week. I've got the little tester.
I'll ask the question everyone's going to ask. When will it be in the store, and what should I do? Should I sign up? What do I do?
The mini vote one, I think will actually be in the store this week. So I got the tester, and I have to put the tester together. And I have to do a couple more things here. This tests, it's very self-testing. So I use one of the outputs to drive a piezo that will test the microphone. There's a couple of GPI. Honestly, it's kind of self-testing because there's not a lot of it is just like, does the Wi-Fi see work? Does it see stuff? Is the output 5 volts level shifted? Does the microphone work? And then you just self-program it. One thing I'm not sure of is, should I ship it with WLED pre-installed? I mean, I guess why not, right? I can install version 1.6.
I say for the first round, go for it, and then we'll hear back from folks, and maybe we would decide not to.
There's one trade-off of of having it with WLED is I can't have the NeoPixel do the rainbow glow thing
out of the box. Yeah.
Out of the box, which I really like because then people can see it's working. So I don't know.
Is there anything else you could put on there at all? Or
it's basically either an Arduino test program or WLED, and I don't know. Some people are like, oh, I have a WLED pre-installed, but it's really pretty easy these days to install. I'm not sure how much effort, and you still have to configure it, right? It's not like, oh, I've installed it and now I'm done. You still have to do.
I don't know. I like the NeoPixel thing because then everything's working.
I like it, and maybe I can have the microphone, something with the LED react to the microphone, so it's like, okay, that the LED, and then some generic NeoPixel outputs on these pins, and I2C scan. So I'm thinking about it. I think I might go with that. It's tempting to have it shipped with WLED, but again, WLED, it's actually a little confusing because it does nothing out of the box, right? You have to configure it. Okay, so the next thing I did is I'm working on some older breakouts that I'm just trying to, you have to get a new product out every week. And some products are kind of big, like this Sparkle Motion, some are tiny, like this little DAC board. It's an Octal DAC, 12 bits. It's a kind of a little bit of a beast. And it wasn't available during the chip shortage, but now it is. I'm kind of trying to figure out what's up with it. It's a little bit funky in that it has I2C control, but also has hardware pins for the LDAC and for clearing all the codes. address select. The I2C interface is actually like very solid. Like you really don't need any external hardware. But the LDAC pin, you're supposed to be able to do an asynchronous toggle to get the output to set. And I can't quite get that to work. And it's like, it should be trivial, but it only works if it's low during the I2C write. And I hate, it's like when I was learning a program and people would say like, it's never the compiler. And I hate to say like, I think it's the chip, but I actually kind of think it's the chip. I think there's a little bit of a weird fluke in the chip design. Because I also saw some other posts online of people who were like, well, I can't get it working the way it's supposed to. So I thought you wanted to do like a oscilloscope
I do.
test. So I thought we could, let me load up, hold on, let me get my oscilloscope logged in here and then I'll put on the, I'll show you how I was testing it. So over in Arduino land, let's do my sine waves. So like I said, can you go to the computer real fast? Well,
yeah.
It'll upload and I can shut off. So I do have to set it for high frequency mode, but you can set it to like 400, 800 kilohertz. I'm just using a plain Arduino. Oops, just set the port. And my little demo here is just to write different frequencies of sine waves. And for like little demos like this, I use ChatGPT to write it because it's like, well, I've already written the library to do it. I just like, I can never remember like the phase, offset, whatever. So then if we go to the oscilloscope.
Scope.
So let's go scope vision. Oh, sorry, wrong way. This is like so slow. So oh wait, so this is just like a simple sine wave. Oh, can you make me a little smaller maybe? Because I'm kind of blocking the.
Yeah, we just did a new setup, so we'll have some adjustments, everyone.
For the scope view, I think I should be like kind of tiny.
Scope view, you want to be tiny?
Yeah.
Tiny.
Oh, great. And then I have like each one be a slightly different and faster. So this is like still kind of slow. And then, oh, you know what? I have debug output on, don't I? That's why I'm like, why is it so slow? Is it? Yeah, I have debug output. Okay, hold on. Let me recompile it without, because I was trying to figure out this LDAC issue again. I don't know what the heck is up with that. I mean, the thing is, it's like I'm still going to release the hardware, even if the LDAC pin works. It just doesn't work the way it should, I think, compared to how every other. Okay, so this is way faster now. So this is, this is 30 hertz, 13. This is, it's only kind of clunky because it's updating all 8 channels. And, like you can do 3 megahertz I2C updates, but I haven't done that. So what's nice is that you can do write an update in one channel. And then there's also like a high speed mode where I think you can like blast data to one DAC if you want. But, 8 channel DACs are kind of hard to come by. And this one is fairly inexpensive, especially over I2C. And I think if you're just doing like, maybe not for like waveform generation, but if you're just doing like, oh, I need offset voltages, or you're controlling a synthesizer and your stuff isn't changing. Like, the voltage is controlling a filter and oscillator. It's not necessarily the waveform itself you're generating. I think it's fine. So what's up with the LDAC? I don't know. I'm going to release the hardware and I might just document it. And it's really rare that there's a chip feature I can't figure out. I don't know. Okay, and the next thing I've been doing, so I just want to do some test view, is, okay, so the TMC 2209, right, which is over here. Let's just go to the overhead. So this trinamic chip, so, we have had the stepper motor drivers for the hand, you have to hand microstep PWM drivers using your, I don't even remember the part number, the TB6612 or whatever, and friends. And then people are like, well, you should have the like ready to go stepper driver chips, like the A4988, which we put in the shop, and then the TMC2209. What's funny is knowing Pedro already did a project. They're like, oh, we want to play with these stepper drivers. They did a project with the A4988 because it came out first. And they're like, wow, this is kind of loud. And it's like, it is. It's like really squeaky. The output of it makes the motor squeak quite a bit. But the Trinamic is like super, it is really silent. So I was like, just try the Trinamic. The Trinamic has two things I like. One is it's got this all-in-one digital control. You use individual pins, so you don't need drivers. You just toggle GPIOs. Trivial to get up and running, to get going. Interfaces with like everything in the known universe. But it does have a separate UART input as well. And this is, I don't know why they use UART. It's a little like, but it's cheap to do your interfaces. It's bidirectional UART. It uses one pin. You can write to it, and then it will flip directions, and then you'll read from it. And it has this, let's go to the computer. Hold on. So I'm like trying to figure out, why is this DAC not working? This is the DAC. Here's, okay. So, it has like what we would call registers, and shift this over here. Okay. It has registers and individual bits in all the registers, but the registers they're not I2C or SPI like I'm used to, and so I was like, I don't want to like there were existing drivers, but I look at other drivers and I'm like, man, I really could do a better job at this. So instead of writing like a UART level interface, what I decided to do is take the BusIO library, which I wrote after we did CircuitPython, because I was like, oh man, CircuitPython had a really good idea of this like generic interface for, a interface where it handles the bit shifting and masking for accessing registers on sensors and devices, which is infuriating work, extremely bug prone, and like very taxing mentally, because you're constantly like, oh, I want to mask off these 3 bits and shift them over 4, and then you have to do the opposite, and then you have to remember if it's assigned, unsigned, whatever. I was never getting it right, and so we have this idea of a register where you can define a register over I2C, the address and the address width, because sometimes there's 16-bit address widths for devices, and then how many bytes are readable, and the byte order is it LSB or MSB, and then it will like do the like the generic SMB I2C interface for reading and writing registers, and then you can have this idea of having bits which allow you to read and write a number of bits that are shifted within that register. And that's what abstracts the like bit masking nonsense. And, it's like some people try to do this with union structs, and God bless them, but then compilers like sometimes freak out and they're weird and it's annoying. And it's kind of elegant. But honestly, I just prefer to have this structure, because also sometimes it's I don't know. I've had iffy experiences with union structs. They're extremely beautiful and elegant when they work, but sometimes they don't. And sometimes they don't fit evenly into, like sometimes they're 24 bits wide, and then it's like, well, it's a 32-bit, but then you have like a buffer. And then dealing with MSB versus LSB, it's also not always obvious how to deal with it. So anyways, register bits. So I finally, I've been meaning to do this for a while, I made a generic device. And the generic device is, instead of just using the wire or SPI device interface from Arduino, which is like well-defined, this allows you to set up a generic interface with function pointers that will read and write a register. So you send it the buffer and the length and the address size, it does all that register part. And then what's cool is the register bits part will just like magically, it just magically works. It's like, oh, it's a type of a register. And like, that's cool. I have access to the ability to read and write a register through this generic interface. And to do this, I was kind of like not looking forward to it. And then at first I was like, oh, maybe I'll do like lambdas within C++. I don't know. I was thinking, I was kind of in like oh, I can have the context within it. And then turns out I was like, the next day I woke up and I was like, what was I doing? And so we actually pass the object variable, which is the object that encapsulates the interface for the generic device. Okay, what I'm trying to say is when you go to, so that's the generic part. And if you go to like actually, I don't know if I committed this code. Yeah, I didn't commit this code yet because I'm still noodling with it. Do I have this code open? I don't have this code open. So let me go here, go here. Okay, so not here, but here. So I have within the class, the TMC 2209 class, I have all the getters and setters that I ended up writing, but they also have the UART stream and then the generic device that's created, and then the UART protocol interface, which allows you to read and write a register, and then the pointer to the TMC 2209 object. And why do I need to do that? At first I didn't, and then I realized it was working fine. And then I realized like, oh shit, there's like address. There's an address for the UART, so you can have more than one stepper driver on a UART pin, which is like, I guess, kind of cool. Although like they could have done this with I2C, but whatever. And so like you have to have context. It's like not only did you have to have that stream object, but now you had to have for each instance of the TMC 2209 an address that you would use when you send the commands. And so that's when it was like, oh, okay, I have to have some context. So for example, to read and write data, so let's show like UART read. The generic device interface for BusIO gives us this pointer. We cast the pointer to our existing device type, and then we can access the UART stream, read as much as we want, do some debug prints. I was debugging, read the data, and return true or false based on whether we succeeded to do that read. Did it with a write, we do the casting. And then you can see here when we're doing the register reads and writes, I have to access the device address. So again, that's the context from, I can't have just this global UART or global address. I have to have it within the object context. But in the end, this actually worked really well. So now it's kind of interesting. And so I don't want to go and refactor the I2C and SPI to do this because I really feel like that works really well. I don't want to fuck with it. But it's an interesting, it's a good idea because there's going to be other weird devices that have like one wire, or they have like, the HX711 chip. It's like, it's not really SPI, it's SPI-like. I don't know. There's always weird underlying protocols that people use. So that's cool. And to do this, I ended up using Claude, which I've never used before, but I had some folks say like, oh, try it out. And so Claude's kind of interesting because it's also an LLM. Everyone's doing these LLMs. And I've been using ChatGPT to do, and I still use it a lot for like, I just need a snippet of code I need to do this testing, and I always look at the code and I read it and I test it and I debug it, but it just like saves my wrist from the typing part. Or copying and pasting, and then I make a, I don't copy and paste properly. I forget to update something. So what's interesting about Claude is it definitely seemed to have like a higher level understanding. It seemed to be like smarter, and it hallucinated less. It wasn't perfect, but it did seem to have a more advanced understanding of the code I was writing. Like I was able to talk about this stuff with function pointers and how, and it just kind of like managed to like get around. And then I was like, in the end, when we redid this code and I ended up passing the object pointer. I said, can you refactor all the code that we've already written? And it was like, oh, no problem. And it did it perfectly. And it didn't like, sometimes if I ask ChatGPT to do stuff, it kind of like ends up finding, it kind of goes off into a ditch. So Claude didn't do that. I definitely, you have to still kind of like tell it where to go, but you're not like constantly, it's not huge zigzags of capability. It kind of has a more narrow, advanced way of understanding the code and writing it. However, the one thing that Claude can't do, which is a little bit of a bummer, but hopefully will be fixed soon, is what I love to do when I'm working on a chip is I upload the data sheet or app notes. And I say, read all the data sheet and app notes, because like you never know, there's an errata, there's like a sub note, there's a footnote, whatever. And then with ChatGPT, I do that and I tell it, okay, make the register definitions, make the functions, whatever, the setters and the getters. In Claude, the context window is much smaller. And so if I tried to upload a PDF, it was like, if you upload this PDF, you're going to like end your chat session because you have exhausted the context length that I'm permitting you to do, which is interesting because like I remember ChatGPT used to just forget earlier messages. Like they would just move the window forward and like whatever you did at the beginning, it would just forget. With Claude, it's just a smaller context window. But hopefully, because a PDF is really big, but I'm not going to section off the PDF, right? And I can't copy and paste from the PDF because it's formatted. So right now, what I'm doing, which is funny, is I'm using, when I'm writing, this TMC 2209 code, is I use, in other libraries, is I'm using Claude for kind of for the more complicated structural decisions and code that I then check and verify. And then I'm using ChatGPT for the like scut work of like, okay, we're going to just write like 50 setters and getters and like look through the library, the PDF, and then just make all the register bits and then like cast it, return, do all the little, and the debug prints and everything that is just a pain in the ass to do. So I'm really liking Claude. I'm recommending it to people to try out. It's good at writing code. And I really like it's a lot more concise. I really like the output. ChatGPT, it's like no matter how many times I tell it, like I don't need you to explain every line of code. I know what to do, just give it to me. It keeps kind of reverting eventually into this like flowery description, whereas Claude is a lot more like on the ball, just do the job. So I have like 2 interns now, right? But like one has a short-term memory, one has a long-term. That's okay. Okay, so that's what I'm doing. How are we doing on time?
You're up to 23 minutes.
Oh my God, that was a long chat. Okay, so let's do a quick desk of Ladyada. Sorry, great search.
Okay.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey and Adafruit. Every single week, Ladyada uses her power of engineering to help you. Yes, you. Find things on digikey.com. Ladyada, what are you looking for this week?
Okay, so this week, let's go to the overhead real fast. I'll show off my stepper motor driver. I've been working on these stepper motor drivers to drive bipolar stepper motors using the TMC 2209 and friends. There's like the 2130. There's a couple other chips I'm looking at from this family, but I'm kind of getting like, I kind of got like the best, right? It's like I don't have every peanut butter, but I have like the 3 peanut butters everybody wants. And so now people are like, well, if you're getting into motor control stuff, we have some requests for you. We want you to do some brushless DC motor drivers. And I'm like, I have never done brushless DC motor stuff. A lot of it is honestly used for like robots and quadcopters, which is cool. I've just never like done those. I mean, yeah, I've just never built my own scooter. I'm kind of like scared of anything over 20 amps, to be honest. It's like, that's a lot of amps. But these little brushless motors are used for fans, used for like quadcopter motors, used for robotics and stuff. I thought, maybe it's a good idea for us to stock a really good, easy to use, getting started, your baby's first brushless DC motor driver. So I thought I would go over, and then I did get one thing that people kept, like a couple people asked for FOC, and I'm like, I have no idea what that is. So I do have to look what that is. It's some sort of like, I think a feedback control mechanism. which makes sense. One thing I've noticed as you're looking at chips is like, what are the features that are available? One thing that is nice is that apparently you can get ones that are sensorless. So like older motors you'd use, I vaguely remember this from like my 6115 lab, is you would have, you can use Hall effect sensors to detect like where is the motor spinning, but you can also use the back EMF as a sensorless way to detect like, is the motor moving? How fast is it moving? And if you want to stabilize on a speed, for example, you can do that because of course the speed is like these brushless motors, the speed is going to be so variable based on the voltage and the wind and the humidity and how it feels that morning. So let's find on DigiKey a brushless DC motor driver. And I'm lazy. I want it to have the FETs inside already. I don't mind adding, maybe if you have to have some protection, whatever on the outside, some flyback diodes, but I really want at least the FETs to be on the inside. And I would love to have digital motor control like the TMC2209 and friends. And it would be really, really cool if I could do that like over I2C. Because it's like I'm getting used to just doing stuff over I2C. And having an I2C controller, and then a fair amount of current and a fair amount of voltage, and then we'll see where we end up. So let's go to the DigiKeys. Okay, so we want to search for BLDC, brushless DC. I have to say that out loud because it's so easy to mix up all these characters. Okay, they have motors. I will have to get a motor. Maybe next time I'll get motors, but a lot of them are fans. It's true. Let's get a motor driver controller. So a lot of options. So first I want to start with, of course, only active stuff. This is an active product we want to design, and I want to have something that's normally stocking, and I'm going to exclude marketplace for now. So that gets us down to like 500-ish out of the 1,500 available. Looking good. A lot of little options here. There's like low cost ones. There's this is clearly part of that family. It's the 4988. They also have the 4931. That's kind of cool. Maybe I'll check that out later. And other DC motor drivers. I definitely want one that's only surface mount. And motor type, I want brushless DC. I mean, these all kind of are. Maybe I'll just clear this because it doesn't really matter. And the interface. And so a lot of them are like SPI or step direction or something. But like I said, I really want to see if I can get one that's I2C. So let's search for I2C, and that filters them out, and then I'll select all of them. And that gets me down to like 50. There's not a lot. And then finally, general purpose, what I want, as I've learned from the stepper motor drivers, is I want the fully integrated version, because that's what I got for the TMC2209 and the A4988. I don't want external FETs. Cool, you want 50 amps? Get your external FETs going. I'm going to do something chill. Again, babies first motor driver. Okay, so now we're down to 30 options. And all these options were actually pretty good. A lot of different companies. Maxim's got some options. This one is actually kind of limited though on the voltage, which I didn't like. It was really low voltage, so I thought maybe I would. I want it to be at least up to like 12 volts, I think, or 8 volts. So I'm going to just filter out all these like 3 to 5 volt only motor drivers. I mean, I'm sure there's a reason to use them, but I want to limit that. Then there was current output. So 250 milliamps is crazy small. That seems really small. I don't think it's that little, but maybe it is. But I like some of these are like 2 amps, 3 amps, 4 amps. And then I tried, filtering by price. I'm not that price sensitive on this because, they're not going to be that inexpensive. You do get a lot. And there are a couple options. You get Allegro. And they have, like, again, this FO, what was it? The FOC? This has, sensorless. You don't need, you don't need to have sensors on the motor to tell where it's at. And then I saw this DRV 10975 series come up a bunch. And this looks really good. It has up to 1.5 amps, I2C, back EMF control. Like I said, you don't have to have, sensor stuff, external sensing stuff. Built-in, step down, all the thermal, whatever, for fan control. I like to look at this application schematic and I'm like, yeah, there's just not a lot going on here. I like that this has speed and direction as well as I2Cs. This one looked really good. I'll say, by the way, I'm not even though I'm picking one in the end here, it's not the end all be all. I might actually make one for a variety of these drivers. The one that I thought was really nice that also had this thing that people are asking for, the MCT, hold on. These were very confusing because there's a lot of them. The MCT, we no longer filter by price. Sorry, the MCF series had the sensors field-oriented control. Again, I don't know what that is, but I've been asked to make one with this. So I'm probably going to go with this to start. Another thing that's really nice about this one is 8 amp peak, which is like huge. You can do speed over PWM analog or I2C direction brake. Has the MOSFETs built in, 8 amp current output, can do 4.5 to 35 volts. This is like kind of a nice little beast, built-in LDO, built-in buck. A lot going on here. It's, not cheap, but it looks like there's it's in this family. So this is the version which has that feedback control system, and this one doesn't. So I might start with this one and then upgrade to this because this is clearly, hopefully it's actually pin compatible to the MCT and the MCF. But this one's less expensive. I can start with this. So this doesn't have that feedback control, but it does have sensorless, and it has that same interface. And then as I kind of get used to using, it's kind of cool. It has a variable monitoring with a DAC. As I get used to working with BLDCs, maybe I will upgrade to that 8 amp version, which is like a little scary, but also looks like a pretty cool chip. So I'm going to start with this one. A lot of really good options for the BLDC. Like I said, I might end up going through and doing the rest of them, but I'm going to start with this one, the MCT 8315A, and then bump up maybe next time to the MCF 8316, part of that same family. So good stuff coming if you like brushless DC motors.
That's a great search.
Where in the world is that part I need? The great search with DigiKey.
All right, that's the show. We got a bunch of stuff going on this week. Tune in, turn on, share, and learn.
Keep your brains going.
Bye, everybody.
Keep your hands busy.
Yep.
Bye, everybody.